This table summarizes all of the substituent group effects. It's arranged from activating to deactivating. In other words, how is it going to affect the reactivity? We go from the highest increase in reactivity, we call that a strong activating group. We go down to a weak activating group. We have benzene in the middle because remember, activating is always compared to benzene. Then we have weak deactivating groups, which only make the ring a little bit less reactive than benzene. And then we have strong deactivating groups. Starting at the top, strong activating groups are going to be ortho-para directors because they are resonance donating. They're going to stabilize the ortho and para intermediates and make those pathways faster. Now, over here on the right is a list of some very typical common activating groups that we might see. These activating groups are characterized by a particular structural feature. They all have either a lone pair or a carbon-carbon pi bond, just a little typo there, on the on the atom that is directly attached to the ring. So for example, if we had an NH2 group, there would be a phenyl group right here. Lone pair on the nitrogen would be able to interact with the cation. What I recommend is that you understand this characteristic because it is possible to see other groups besides the examples given. And I would expect that you should be able to use the characteristics to place them into the proper category. Weak activating groups are also orthopara directing. They are the inductive donators. Remember that I said the inductive effect is smaller than the resonance effect. These are generally the alkyl groups that are alkane-like. So the ones that are alkenes directly adjacent to the ring or phenyls, aromatic rings are actually strong activators because they can do resonance. So this would be like methyl, ethyl, T-butyl, or any carbon chain that had essentially an sp3 hybridized carbon directly attached to the ring. The halogens are very interesting. These are weak deactivating groups. The reason for that is that they kind of have a conflict. They're inductive withdrawing because they're generally very electronegative. And so if we look at the bond polarity, we would see partial negative on one end, partial positive on the other end. But they have lone pairs, so they can do resonance, although the resonance becomes pretty weak with the much larger halogens. So in general, what we see then is they make the ring slightly less reactive, but they do favor ortho and para because of the resonance stabilization of the ortho and para intermediates. So they're weak deactivators, but ortho-para directors. Finally, then we have the strong deactivating groups. These are groups that would be the E groups in the Diels-Alder dienophile that we talked about earlier this semester. Strong deactivators, as we saw from the energy profile above, are meta-directing, and these are generally completely withdrawing on every scale. They're inductive and resonance withdrawing. Here's a list of the common ones. NO2 is a particularly common one, C triple bond N, anything that has a carbon oxygen double bond directly attached to the ring. What these have is a positive formal charge on the atom attached to the ring in at least one resonance form of the group itself or of the reactant. So, putting this all together then, if we're given a single substituent with any electrophile, doesn't matter what the identity electrophile is, we look at the substituent, we find where it is on the table, and that should tell us which regioisomers are going to be preferred. The last part of this then would be looking at what happens if we have two or more substituents, because in that case, they might not agree. So we're going to have two rules to deal with this. The first rule is that the regiochemistry of the effect of the most strongly activating group takes preference. So strong activating groups, because they make those pathways react faster and the faster pathways are preferred, they're always going to lead to the preferred products. So when I talk about the strongest, most strongly activating group, what I'm really talking about is going up to the table and just comparing where the groups are on the table. The higher on the table, the stronger the activating group, the more preferred that product will be. The other thing that we need to be aware of is that there is a steric hindrance effect when we have groups that are meta to each other already attached. So if we have two groups that are meta to each other, it's going to be very hard to fit the electrophile between those groups. It's not impossible, but it's going to be less favored. So if there are other options, the group will go somewhere else. If the only place it can go is meta, then it will actually go in between, or in between those two metas, it will go in between them. Let's look at two examples really quickly with a problem-solving strategy. So what we're going to do here in this strategy is we're going to look at the two groups that are already attached. We're going to indicate with either a shape or a color those two groups, and then we're going to draw arrows to show where would those two groups like the incoming electrophile to attach. So for example here, I have this methyl group. I put it in a blue square. The methyl group is an ortho-para director. So it would prefer to have the electrophile attach either ortho, which would be these two positions, or para to itself. Now when we look, I drew an arrow pointing to those positions. I labeled them with the symbol. But when we look at this one in the para position, that's blocked. It's blocked because there's no hydrogen to replace. So we can cross that one out. When we look at the nitro group, the NO2 group, I put a red circle. The nitro group prefers for the incoming electrophile to attach in the meta position to itself. So here's the group. We start at the group. We count over 1, 2. That's meta, right? So 1, 2, 3. Meta related. So that would actually be in the same position as the ortho to the blue group, to the square group. So we put those two right there. What we would conclude then is that the groups agree. Both of them want the electrophile to come into one of these two positions. This would be our preferred product. We would also get a product where the nitro group was attached here, but we could just flip that over 180 degrees. It would be the same thing. In contrast, if we look at this reactant, which has the methyl group and the nitro group meta to each other. Again, methyl group will have the blue square. We go ortho and para to the blue square to where it's attached. We get these three arrows. We're going to cross this arrow out because it's between two meta-related groups. That's disfavored, sterically disfavored. Now when we look at the red group, because it's moved over, the meta to that group is in a different location. It's actually starting here, 1, 2, 3, 1, 2, 3. So this position here is blocked because again, there's no hydrogen to replace. This position is a possibility, but what we would conclude is that the nitro is a deactivating group. The methyl is a weak activating group. So therefore, the weak activating group would take precedence. So we'll cross out the red arrow, and we're left with these two arrows. So we would get products where nitro attached here and products where nitro attached there. So using this problem-solving strategy then, we should be able to predict the preferred regioisomers of most of the possible reactants that we